time. All right, so our job, our goal right now, review from last time, is to illustrate and explain 3/2 plus 2/3. This problem we could do with the pattern blocks, or we could do it with square cakes. I prefer square cakes. With you guys, pattern blocks are fun to play with kids because they can pick them up, they can manipulate them with their hands. What do you want to do, pattern blocks or square cakes?
I like the cakes.
Excellent. That was my first inclination. So to do this, I got to remind myself as part of my explanation. What does addition mean?
Combine and count.
That's part of my explanation.
I said combine and count.
Yeah. Add means combine and count. So I expect you to tell me what addition means. Or if it's a subtraction problem, what does subtraction mean? Like maybe you'll say subtraction means to compare and find the difference. All right, what else do I need to explain? I need to explain what a fraction means. What's a fraction mean? Equal part of a whole. Okay, so a fraction is an equal part of a whole. And Summer out there on the internet, is my voice fading or is it still clear when I'm writing on the board? You could just write good or you could write bad and I will change my mode. It's okay. All right. All right, so we got those things down, and so if fractions equal parts of a whole, then I should be able to draw a whole and show what the fraction are, each fraction is, and then I should be able to somehow combine and count. So now I start to work. I have to show 3/2. Okay, so let's see. I start with a whole, and I need to work with halves. So there's 2/2. What do I got to do? I need 3/2.
Make another cake.
Draw another hole. You could get away with drawing just the half, but I'm going to draw a hole. Oh, that doesn't look like a size, does it? Close. So I mentioned before, some days I need to work with graph paper. All right, so I have 4/2. I'm just going to be clear and say, hey, these are the 3 that I'm working on. So 1, 2, 3. Okay, so I want to combine that 3/2. I'm just going to put a little plus to indicate my addition or my combining. Now I have to draw 2/3. And my advice to you when you use the cakes is that'll do. Once you draw the first one vertically or horizontal, go the other direction for the other one. So I'm going to go horizontal for the next one, thirds. So I cut thirds, and I want 2 of those suckers. And hopefully we recognize that there are 4 pieces there, so the answer is 4. That's a joke. That's not true. Okay. So the problem is what with these pieces? Are they all the same size?
No.
No. So is it okay to say there's 4 pieces? Sort of. I mean, and if I gave each of you one of these pieces, would you all feel you got an equal amount? No, right? So in the first picture with the 3/2, yeah, there's 3 equal parts of wholes there, and over here there's 2 equal parts of a whole here, but they're not equal parts with each other. So now we have to do something about that, right? We are not able to count accurately because we can't combine unlike things. Otherwise, the best I can do is say, hey, I've got 3 things that are halves and I got 2 things that are thirds. That's what I got. But we want one single answer. So what we have to do is cut each like the other. So I'm going to make a little note. Since pieces are not the same size. So this is what I mean by explain, right? You got to tell me why you're doing what you're doing. I can see that stuff happen. You need to tell me why. So cut each like the other. So the halved cakes need to be cut into thirds, and the third cake needs to be cut into halves. All right, now I have a whole bunch of pieces. Let's see, 6, 7, 8, 9, 10, 11, 6, 7, 8, 9, 10, 11, 12, 13 pieces. Does anyone else count 13? Are all of these pieces the same size?
Yes.
Yeah, the first time I tried to count, they weren't the same size, so my counting was not good counting. Now I can definitely say I have 13 things. What are those things? 13 whats? What is it? Okay, so what's special about them? Anything? Are they halves? Do I have 13 halves here? Do I have 13 thirds here? Or do I have something else?
13, 6.
Why
There's
6?
6. It's divided up evenly. Into
A whole
6.
has 6 equal pieces here. Yeah. Remember, what do we define fractions to be? We define fractions to be equal parts of a whole. How many pieces are now in one whole? 6. So this has to be 13/6 is the answer. So that's one answer. A lot of people don't like improper fractions because they're improper. We got to do something about that. So there's another version of this answer. What's another version of this answer? 2 1/6. Do I have a picture of that here? No. Okay, so what I need you to do next is justify with a picture that 2 1/6 is the answer. So I'm going to let you try to fill in that next picture. I could just write 2 1/6, but
okay.
I don't see why. I need you to show me why, or state why. At least 2 ways to do that. Okay, so one way to do it is to just rearrange the pieces into as many whole blocks as you can. And so I count them out, right? I get 1, 2, 3, 4, 5, 6. I need to get to 13. 7, 8, 9, 10, 11, 12. Ah, there's 13. But this picture shows something a little different. What does this picture show clearly? How many holes are there? There's definitely 2 holes now. And there's 1 out of 6 left over. So 2 1/6 is also another version of this answer. So we regrouped our counting.
So all this works as an explanation?
Mm-hmm. Yeah. So what, and here I could make a note because I don't know what you're thinking, so you want to be clear. So I spoke this as I did it. So what could I write on paper here? Count or maybe recount these pieces into holes, and note extras. Right, so here's my 2 holes plus 1 out of 6 is my extra. Okay, one way I could word that. We could do a more mechanical version of this that's less picture oriented, which I don't think is as good, but you know, I can say, hey, 6 goes into 13 twice with 1 out of 6 left over. I like the picture version better.
With long division work to show.
Yeah, so I'm
saying to
writing
show
out the
that
result of the
instead-
long
Shouldn't
division.
that say
But
13?
with yeah, long division would be fine too. 6 goes into 13, 2 times
Like 1 over 6.
1. Yeah. So then that leads us to write 2 over 6.
But then, like she said, it's gonna be a 13 instead of a 12 up there. Like 6 goes into
Oh,
13.
oh, that was supposed to be a 13. Sorry. Yeah, right. 6 goes into 13 twice with 1 over 6 left over. Thank you. Typo. Yeah, so illustrate and explain. What I'm looking for again is you to tell me, hey, what does addition mean and what are the things we're adding? And then show me with a picture how to put them together. I could have drawn the same thing instead of using the squares, I could have drawn the hexagons. And in this case with the hexagons, I would be using the, let's bring up hexagon picture. Here and here and there and there. Oops, wrong one. Those are color tiles. Oops, I don't want color tiles. I want, yeah, where did I put that? Activity 2. There we go. Yeah, so here, I would say maybe this is a hole, and I would label it as such. And then I would want to show 3 halves. So 1, 2, oops. And so this could be my 3 halves, and I would label it. And then I want to combine that with 2/3. And so then I have to manipulate these toys then to come up with an answer. Because I could just say, hey, there's the answer, blue and red. But that's not a complete answer, right? I have to do some more work. So what would I do here to make this work out? If I were going to use these toys to come up with an answer.
Convert them to triangles.
Convert them into triangles, yeah. So the next thing I would do is I would just trade in each of those and say, let's do it with triangles instead. So I get a whole bunch of triangles out, and I start putting them in there. Yeah, so we'd replace them all with triangles, and then we could come up with an answer. So let's flow through this just to see it. Do you have these toys in front of you?
Mm-hmm.
So hopefully you grabbed enough that you should be able to build this particular thing. And you should have enough triangles too. Summer at home, if you don't have these toys, I have a link in activity 5.2. Part 2, there's a link to the online toy I'm playing with for pattern blocks. And when you first open that, your browser may object to it, and you may have to push a little button that says, hey, let Flash load. Okay, so I'm going to rebuild them. I think I'm going to do it underneath. And does it let me copy groups of stuff? Oh, it copied everything. I forgot about that. Darn it. Go away, please. Can't, oh, there we go. So the online ones are not quite as easy to play with as the real ones.
with certain young kids I know that are working on fractions, this would not be a fun toy to play with. Although most young kids I know are pretty damn good at video games, so this wouldn't be too bad, I guess. Okay, so I just recreated it there. So let me grab this screenshot. Because this requires some explanation, so I need to doodle a little bit to go with this.
And so what would my explanation look like here? It's going to look pretty similar. So I, up front say a fraction is in equal parts. In this case, I'm going to be more specific and say of a whole hexagon, because I'm letting one hexagon be a whole. So I'm going to write that a little bit different. Addition is combine and count. So if this problem is on the test, you could use either the square fractions or you can use the pattern blocks. And then here I'm trying to show my 3/2 plus 2/3. But these pieces are different sizes. So I could just say there are 5 pieces. That's my answer. Is that a good answer here?
No.
No, it's not a good answer. Because there's red pieces and they're bigger than the blue pieces, which are smaller. Right. So trade red and blue, blue or green. Now that rewrites my my numbers here, so I'm actually going to be a little more explicit than last time. Instead of calling the first number 3/2, what should I call it instead now?
1 1/2.
Nope. That doesn't help. Yeah, 9/6 is a better answer because there's now 6 parts of a whole. So what I'm illustrating now is 9/6 plus
4/6.
4/6. And would you agree, now that I'm playing with the green pieces, I have 13 pieces altogether, and they're all the same size? So I have 13, and what are those? Each of those 13 things? They are 6. Yeah, so remember the numerator always means your count. And it only makes sense to count like things. The denominator is your description. What are you counting? In this case, we are counting 6. So there's one quick answer. What would we do to get another answer like 2 and 1/6? I'm not saying it's a better answer. I almost did accidentally. It's not necessarily better. Exactly the same thing we did before. We try to make as many hexagons as we can and then see what's left over. And that would allow us to state the 2 and 1/6. All right, better? A little, maybe? Still feel resistance.
No.
Feel your energy field.
No.
Feel fraction resistance. I'm just teasing, sort of. A little bit.
Explain resistance.
Explaining resistance? Yeah.
It's tough. It's just tough to
Yeah.
have what you're, if you like doing it in your head and you know what your process is, to actually put it in words if it makes sense on
Yeah.
words.
So that's, you mentioned the word process, and this is more than just a process, right? We're trying to get physical and show how this has got to be the answer, right? I can't, because somebody, like, why couldn't somebody say 3/2 plus 2/3 equals 5/5 instead of 13/6? Can you see how somebody might do that?
Yeah.
Right? Wouldn't they go 3 plus 2 is 5 and 2 plus 3 is 5? Why not call it 5/5? Is this bad?
Yeah.
Sort of. I'm using a different kind of addition. Do we ever do addition like that?
No.
No fractions. We kind of do. Okay, so that's not a, this isn't a good example. Let me do a better one. Suppose we had 3/5 plus 2/3. Let's do that one instead. And I'm going to circle that addition because this isn't regular addition. But I'll give you a reason that this works. 3 plus 2 is 5, and 5 plus 3 is 8. So I play baseball, and the first game I got up to bats 5 times and I hit it 3 times. Second game, I got up to bats 3 times and I only hit it twice. What's my batting average?
5/8.
5/8. Yeah. So it turns out, although these are, I'm adding ratios, this is a special way to add ratios. It's not normal adding fractions. There are times in our lives we do that. But that's not what a traditional fraction means, right? So that's one reason it's important that we state what are the things we're adding and what does addition mean. You got to be upfront about those two things. That helps us guide the answer. Okay? So the first step, anytime I ask to illustrate and explain, is tell me what are the things we're playing with mean physically, and then what does the add, subtract, multiply, or divide mean physically. Name those two things out front, and the rest kind of flows from there. All right. Any other questions before we go on?
Can we do number 18 from the homework?
We can try.
Let's see, shift desktop, homework. I gotta reload that in a sec. Number 18. 18. All right, so we have negative 5 7/8 plus 6 5/8. This is the type of problem
Yeah.
you came up with?
A
Okay.
negative plus a positive for fractions.
All right, so we get to play with sign numbers and fractions. And let's see. I'll screenshot you. New page.
Yeah, because you just add your whole numbers and.
Okay. So a couple things to think about here. Last class, was I in favor of working with mixed numbers?
No.
Or not? I was not, right? So the first thing I would do here is rewrite this as improper fractions. So I would take the 5 times the 8, and then I would add on the 7. And the negative is just hanging out front. Just kind of ignore it at first. So 5 times 8 is 40 on a good day, 47 eighths. So this would be negative 47 eighths. And then this one over here, same routine, 6 times 8 plus 5 is 48, 53. That's all right? 53 eighths. Hey, these have the same denominator. That makes it kind of nice. So all I have to do now is figure out what's negative 47 plus 53. And I'm pretty sure that's 6.
Yeah.
So the answer here should be 6/8. But we are good students of fractions, and we'll probably decide to reduce this by dividing by 2, top and bottom. And so that would be 3/4. Seems like a good answer here. Okay. Now, if you tried to do this without, there's a little trick that's important I mentioned the other day. When we read a fraction like this one right here, we read it as 5 7/8. Okay. When we put a negative in front of a number, like instead we call this negative 5 7/8. A negative really means negative 1 times 5 7/8. And 5 7/8 is really a more complicated thing because there's a plus sign. And because of that plus sign, we have to insert parentheses to assert the order of operations, which means I kind of have to distribute that negative 1, which means this number right here could also be written as negative 5 minus 7/8. So if you tried to break this up and you accidentally tried to think of it as -5 plus 7/8, that is not that number up there. They're not the same thing. So mixed numbers are a problem for a lot of reasons. They're good for communication, giving directions, measuring stuff, but they're not good for computations. Can you still do computations with them? Yes, but it's almost always harder. All right. So easiest thing to do is just make them improper, and then the problem's not so hard. Does that help? Yeah. Other questions? Yep.
One quick question. If you're doing that problem that we did earlier, but the denominator is different,
Yeah.
can you do it with a mixed number and then just reduce it at the end? Or like,
Let's do one with the mixed number and try to figure that out. So if you had some, do you want me to throw negatives in there too?
sure, why not?
Okay, so suppose we had negative 2 1/2 plus 4 1/3. How about that one right there? Okay, so first thing I would do is improper. Is that okay?
Mhm.
Yeah, so I would say 2 times 2 is 4 plus 1 is 5/2, but it's negative. And then this one over here, 4 times 3 is 12 plus 1 is, oops, this was plus, sorry. So that's 13/3. And then what I would do here is just use my arrow method. So I would just say 2 times 3 is 6. 3 times -5 is -15. 2 times 13 is 26. They're being added. So -15 plus 26 is 11. So the answer should be then 11/6.
I like that method a lot.
Yeah. So I'm a big fan of the arrow method. So if your curriculum, if you end up being a fraction teacher, and some of you will and some of you won't, if your curriculum just focuses on the LCD method or the LCM method, and you have some kids that are just really struggling, show them the arrow method, right? It may be there's a standardized test that's going to ask them questions about the LCD algorithm, and they might not get those right, but they can add fractions otherwise, and that's more important. So unlike last quarter where we did some weird algorithms for addition and subtraction we probably don't want to teach the kids, this is one that should be taught. So if it's not in your curriculum, definitely remember, oh yeah, I remember that method for doing it. It's a good one. And this is included in most curriculum these days, it shows. But the LCM method is also still taught. Okay. So you might say, well, why even bother doing the LCM method if it's so hard sometimes? The answer is, it is necessary for algebra, and there are some kids that are going to need algebra in the future. Any kid that ends up doing some science tech kind of degree in the future, they need algebra, and the LCM is important. Could they learn it when they need it when they do algebra? Yeah, they could learn it then, but it's complicated. It doesn't hurt to see it early. But there's a way out. Okay, other questions? All right, let's play with multiplication. So let's do a couple of examples first, and then I have an activity for us to do. Page. And I am going to stop this recording and start a new one, but that won't hurt anything for you, Summer. Stop recording. Do you want to stop the cloud recording?